Hi, good afternoon. I'm Pollyana. This is Leonardo. We are structural engineers. We are from Brazil. And we bring to you today our research about image processing for continuous monitoring of cracks in civil constructions. I know that you all are anxious to see the code, but first I'll talk about a little of engineering so you can see the importance of this method. Just a minute. Crack. A crack is not just something ugly in the wall, like you see, but the crack also could be the way that the structure shows us that something goes wrong. And it's very important to monitoring to see if there is something that could be a danger too. The cracks might be caused by plastic deformation, thermal expansion, or chemical reactions, and the width of cracks is an important parameter that we use to class them and know the danger that it represents to all structure. Here we can see a little spoiler of our research. So the first step to protect the structure is identify the crack. Oh my God, is identify the crack, and after we monitor the development to know if it's established or not. I guess everyone here has seen a wall like this. This is the visual inspection. But the ideal case to identify a crack is when it's a small crack that we cannot see with the naked eye. So we use the microscope or some equipments that use waves to identify small discontinuities on structure, and we can identify a crack before they appears. Okay. Today, the main equipment that we use to monitoring the crack is telltales. It is this equipment here. And we can measure the width of the crack over the time to see if a thin crack is becoming a wide crack, and it's possible to know how faster it happens. And now I will talk about the applications because around the world, we have many examples of disasters we could have been avoided with the monitoring of the cracks. Here is an example in my country, Brazil. I don't know if you know about it. It was the biggest environmental disaster in our country. Dam broke in 2015, and here is more pictures of this disaster. And here is a note that says, engineer says he warned Samarco, it's the owner of this dam, about cracking in Fundão Dam. So before the disasters happened, an engineer warned that there is some cracks and nothing was done. And now we know what happened. This is an example near to you in Florida. A bridge fell after they found cracks and nothing was done to. Here some more pictures. And this is this disaster, what happened. And here we have another example. It is to show you that this method is going beyond the civil structural engineer. This airplane disintegrated in the air, and the cracks also were found before. Just a minute. This is not the plane that of disaster, but this is the new that says airplane that disintegrated with parachutes in allentation presented destructions and cracks. So this is a little of the importance of our method, and now we show you.
Thank you, Paul, for your introduction. Our research is in the initial phase. We are very excited about it because it has many applications, mainly to make structures more safer than they are today. In our country, had also another collapse of a dam that killed more than 200 people. So this could be avoided if the monitoring of these structures were effectively done. So the method is quite simple, but the results are very important. So I'm going to show you how we did it. So first, we have some functions to do the text, to put the text on the pictures that we are gonna monitoring of the structures. And then we have some calculations. First, I'm gonna show you the raw video. To monitoring the cracks, we need to take pictures, a lot of pictures of that, or make a movie, make a video. And this video, it can be taken for any period of time. You can take it for 1 day, 1 week, 1 month, or years. So you go processing this information, you can monitoring the crack in real time. So I'm going to show you the raw video. It's taken from a microscope. So in this case, it's about 600 times, okay, bigger. So let's see the crack moving. So it starts to expand. So it's a traction crack. We see here the monitoring with a caliper. So the crack is open. This is just a monitoring for 30 seconds, but it could be any time. So this is the raw video. So we are gonna import this video to the Mathematica, and we can also couple other sensors than the image. We can use temperature, moisture, forces that are going at the same time. So we install sensors and we read that data and get all together so we can do this analysis by a couple ways. So we get the video. We split the video in frames, so you can input pictures or you can input the video. So we get the frames. In this case, we have 365 frames. A temperature, just for example, is this curve. And we get the frames of the video. So here we have the first frame, and here the last frame. And now we have to decide which base points we are going to take for reference. First, we try to use some target for to establish the points, just like we saw in the first slide, like here. We draw some points. We were worried that Mathematica couldn't track the points, so we did these, but it was not necessary. This function, this track function, this worked very well. So we just picked this point. Can you see? Very small. And this point, one of each side of the crack. So we established the coordinates of these points right here. We choose. And we use the image feature track to track the position of these points in each frame. So for each frame, it's going to calculate the position of the frame. It's calculating now. It's running. And then we have to establish the factor that converts pixels to millimeters. So we have a template. The microscope has a template that we can easily convert the pixels, the dimensions of the pixels in millimeters. It's still running. This is a very good opportunity to use parallel computing because they are independent. The analysis of each frame is independent. So we could use a cluster for large amounts of data. So Mathematica can do it very well. So here we have the coordinates of the points. Let's show some more. And here are the coordinates of this point and this point for each frame. Then we are going to calculate the distance between these points, and we are going to overlay the numbers, the dimensions, and the data, the information on each frame. So it's going to be, it's very fast. Then we can export the video, and then we can show the result of this. So here we have the video, and we have the information about the distance. So in the first frame, we have 0 distance between the points. So the crack is at the initial state, and we can go through the frames. So we can see that the value measured by Mathematica is the same than the caliper. We did this in a steel frame that holds a piece of concrete, so we can adjust the width of the crack, and we measured it with this digital caliper, and the results were very good. So here we have the measured crack, This is a traction, so it's opening. And we have the measures. Let me show you the video. We can export each frame and make a video. Here we have the horizontal displacement, the vertical displacement, and the distance between them. We can also add here the temperature or any parameter that is measured at the same time of the video. And one advantage of this method is that you can see the crack. You can see the crack opening. You can see the crack closing. So it's an advantage in relation to the usual methods that only use a sensor that only gives you numbers. So if you have a peak, if you have a strange value, you can go to that frame and see what happened. Maybe an earthquake that shake the microscope or shake the structure. So you can see what happened. You can see if there was water going inside the crack or something around the crack. So, but we have challenges because when we do this by image, we have a 2D system. So if the crack does this, traction or compression, it's okay. But if the crack bends like this, or if the crack moves in the vertical like this or like this, how are we going to take these measures? So maybe there are some solutions for that. We could take the size of the base points. So if the cracks go in this, the point, the diameter of the point may decrease. So there are some solutions for that we may implement in this code. But this is only a part of the work. We intend to use AI to recognize, not only monitoring the cracks, but recognize the width of the crack and to know what kind of crack is that. And if the crack is a threat to the structure, if it's going to cause a collapse or it's going to cause some problem. So we will implement this, and we have some ways to do that. So here we have examples. So we can find pores, holes in the concrete. We can find cracks, and we can also measure the width of the cracks. So the goal here is to use an automated system to monitoring all the cracks of a large structure, a large dam. So we are designing a robot, so it will have a camera, a high-resolution camera, this GPS positioning system, and it's going to take one picture at each millimeter, and it's going to do the diagnosis for the crack. So we can let the robot go through the structure, also climbing a vertical wall, and collect all this information, send to the base, and this is processing in real time. So after that, we can have a map of all the cracks on the structure, and engineers can take decisions about what should be done about that. So that's it. Our project is just starting. We are looking for financial support for that because we have a lot to do, the robot and some, we need also the cluster. So if you're interested, you can talk to us. Thank you very much for your attention, and hope you enjoyed it. I guess we have some time for questions.
I was wondering if you have your cracks outdoors, right? And you're getting water or bird droppings or whatever on there. With the AI, have you tested, can you reconstruct the critical points when you have like debris on there, or is that something to work on?
Yeah, we are gonna work on that because we want to, in this case, it's a microscope picture, but we can also use a usual camera that's gonna make pictures of the area. So we are gonna know what's happening around the crack. So this is also a very good information. Yeah, and this robot in the future it can go underwater or subsea.
Question. In the U.S., most places where concrete is used, you keep a register of who mixed it, what kind of concrete, what additives, all of this. I'm from Mexico City in 1985. We suffered one of the biggest, earthquakes.
Yeah.
And we lost maybe 25,000 people. Just recently I lost, a friend lost his wife, and the architects keep building, corruption. So I wonder if in Brazil there's a record, like a register of all these, public works or buildings, because, like this is after the fact, but it seems like whatever's been built, there should be like a, like a database of who's responsible, because, this is great, and I guess there's a lot of buildings that need to be checked.
Yeah.
But kind of like now forward.
Yeah, we don't have this record.
Right.
Yeah, we have many problems in public constructions.
Corruption.
Yeah, corruption and many problems. Old structures that they don't have maintenance. Right. So this is a problem. But when you monitoring cracks, you have time to take measurements for the strengthening of the structure or to avoid. Yeah, take samples of the structure is one part of the diagnosis. Okay. You can take samples and also do the monitoring of the structure. And this method we can apply not just in concrete structures, we can also apply in ships, vessels, and also in airplane structures. Right. Yeah? You have time for one more question? Yeah?
You had an example of a dam that you put up there. I was wondering if you could, is there mitigation that can be done to save the dam, or is the main point to get people out of the way?
No, it's for the maintenance of the dam. Yeah, it's not an alarm.
Prevented it from being catastrophic failure, then you're saying?
Yeah. It's a very earlier advice. Okay.
For internal cracks, people can use ultrasonics. Have you tried this method on ultrasonic images?
No, not yet. But we have another project.
Get enough resolution with ultrasonics?
Yeah, we saw many interesting papers here that use some tools with sounds that can be used like this. We have an example we have another project that is to do inspections in facade of buildings. So there is a robot, it has a hammer, it goes like this, and by the sound, it knows if there is a problem there, analyzing the sound. But this project, it's just here in idea. Okay? Thank you very much again.